Good afternoon, friends. In this session, we are going to deal with structural dynamics about the topic theory of vibrations. DYF is nothing but degrees of freedom. The definition of DYF has been given over here. It is defined as the number of independent coordinates required to define the displaced position of all the masses relative to their positions. In structural dynamics, mass property denotes the DYF, whereas in statics, the stiffness property denotes the DYF. Let us move on to the examples to get a clear-cut idea about what is degree of freedom. Case 1. In case 1, consider a simple pendulum with an inextensible spring. In this, when a force is applied, it causes a displacement from its original position in which an angle theta will be introduced in between the displaced position. So, theta will be the independent variable to define the degree of freedom in this case. Hence, it is 1. Moving on to case 2, consider the same simple pendulum with an extensible spring. Here, a compression can take place in the spring position and a displacement with an inclination of theta will be taking place over here. So, degree of freedom is equal to 2 in this case, where angle theta and the length of the spring, which is denoted by r, is used to denote the degree of freedom. Moving on to case 3, in this there are two simple pendulums which are connected together by an inextensible spring in between them. In this case, when a force is applied, the two simple pendulums will move back and forth and the displacement will be equal in both the simple pendulums since they are connected by an inextensible spring in between them. Hence, angle theta will be sufficient to define the displaced position. So, the degree of freedom is equal to 1 in this case. Moving on to case 4, here we are going to have two simple pendulums in which they are connected by an extensible spring in between them. When a force is applied, the two simple pendulums will move back and forth and the amount of displacement will not be equal in both the simple pendulum since they are connected by an extensible spring. In addition to oscillation, it also causes an extension or compression in the spring portion. Hence, the degree of freedom is equal to 2 in this case. Moving on to case 5, consider a system as shown in the figure in which a spring is connected to a rigid support and it has been connected to a object of mass m which has a roller support at its bottom. In application of force, say P of t at one end, it causes a displacement, say U of t will be taking place over here in which it defines the displacement at this position. So, the degree of freedom is equal to 1 in this case. Note, the spring which has been connected to a rigid support plays no part in defining the degree of freedom in this case. Moving on to case 6, let us consider a system of forces as shown in the figure in which two objects of mass m1 and m2 are connected together by an extensible spring in between them, and a spring also introduced in between the rigid support and the object of mass m1, in which k1 plays no part in defining the degree of freedom, whereas k2 plays an important part in defining the degree of freedom. In case of application of force, say P of t at one end, it causes a displacement x1 of t and x2 of t at their respective positions, and also an displacement also takes place due to compression or extension of the spring portion. So, in this case, the degree of freedom is equal to 2. Moving on to case 7, considering the above case in which the difference is they are connected by an inextensible spring in between them and the application of force P of t will cause a displacement x1 of t in this object of mass m2, and also the same displacement will be prevailing over here in this object since they are connected by an inextensible spring. So, the degree of freedom is equal to 1 in this case. Moving on to case 8, consider a system of force as shown in the figure in which the object of mass m1 has been connected by an spring to a rigid support and it has been connected by an inextensible spring to a bob of mass m2. When a force of magnitude say P of t has been applied at one end, it causes a displacement of x1 of t. Due to this displacement, the bob of mass m2 will try to oscillate back and forth, which causes an angle of inclination theta between them. So here theta and x1 of t are used for defining the degree of freedom, hence it is 2 in number. Moving on to case 9, applying the same condition as what we have seen in the previous case with a alteration that the object of mass m1 has been connected by an extensible spring to the bob of mass m2, and depending upon the nature of loading, the spring can extend or compress, and due to oscillation the bob may move back and forth, which causes an angle of inclination theta, and extension and compression of the spring portion will take place. It also has been introduced in defining the degree of freedom, hence x1 of t displacement and extension or compression of the spring, which is denoted by the length r, and angle of inclination theta are responsible for defining the degree of freedom. Hence, I would like to conclude that degree of freedom is not an intrinsic property, and it depends upon the nature of loading and the boundary conditions. Either it may be a roller support or fixed support. It depends upon the boundary conditions and nature of loading. Nature of loading in the sense means the force can be push or pull, etc. In this session, I hope you guys may understand the concept of degree of freedom and how it is applicable in structural dynamics. Thanks guys.